Welcome to an in-depth look at the Audi 4L V8 TFSI engine from the EA825 series. This engine represents a joint development between Porsche and Audi AG, building on the foundation of the V6 EA839 series. Not only does this collaboration streamline manufacturing, but it also brings significant benefits to after-sales service, as many special tools are shared between the two engine families. First introduced in Bentley and Porsche models, the new V8 made its Audi debut in the A8, with production taking place at Porsche's state-of-the-art facility in Zuffenhausen. In this video, we'll explore the technical characteristics, unique features, and innovations that set this engine apart, providing a comprehensive understanding of its design and operation. Before we dive into the technical details, let's outline the learning objectives for this session. By the end of this video, you'll understand the core technical characteristics of the 4L V8 TFSI engine, how its oil supply and cooling systems function, the special features of its air supply system, the impact of its improved injection system, and the changes introduced for after-sales service and maintenance. This overview will help you appreciate the engineering advancements and practical benefits that come with this new generation of Audi V8 engines. New Audi V8 engine boasts several advantages over its predecessor from the EA824 family. It features an 8-cylinder V configuration with a 90-degree bank angle and an aluminum cylinder block, delivering high torque at low RPMs. The chain-driven valve timing, 4 valves per cylinder, and double overhead camshafts with roller cam followers ensure improved responsiveness and efficiency. Notably, the engine includes turbochargers with charge air cooling, a significant increase in power and torque, and enhanced fuel economy. It also meets stringent emission standards thanks to its advanced emission control system and thermal management module. Let's take a closer look at the technical data of the 4L V8 TFSI engine, code CXYA. This engine delivers an impressive 453 horsepower at 5,500 RPM, and a robust 486.79 lb-ft of torque between 1,850 and 4,500 RPM. It features a 90-degree V8 design, displacement of nearly 4 liters, and a compression ratio of 11:1. Engine utilizes hot side-inside turbochargers with a maximum charge pressure of 31.9 psi, managed by a Bosch MG1CS008 control module. Weighing just over 500 pounds, it meets ULEV 125 emission standards and incorporates a dual exhaust system with advanced catalytic converters. Cylinder block of the EA825 V8 is crafted from ALSI 9Q3 aluminum using a single sandcast process. Its deep skirt design extends the cylinder walls down to the upper oil sump, providing exceptional rigidity. Weighing just over 86 pounds, the block integrates vital components such as oil spray jets, water and oil pumps, and mounting points for ancillaries. The engine number is engraved on a plate at the front, and a sticker with the engine code is attached to the vacuum pump cover, ensuring easy identification and traceability. To ensure durability, the cylinder walls are treated with atmospheric plasma spraying APS. This process starts by roughening the cylinder surface with a dovetailed pattern, allowing the APS coating to adhere securely. A plasma torch then melts powdered iron, spraying it onto the cylinder walls to create a robust wear layer about 150 micrometers thick. This advanced coating, similar to 100 CR6 bearing steel, provides excellent wear resistance and longevity, supporting the engine's high-performance characteristics. Crankshaft is supported by 5 main bearings, with the upper bearing bosses integrated into the cylinder block. Gray cast iron bearing caps are secured with both longitudinal and transverse bolts, ensuring stability and strength. This robust arrangement minimizes vibration and supports the high power output of the V8 engine. The precise engineering of the crankshaft and its bearings is crucial for smooth operation and long-term reliability, especially under the demanding conditions this engine is designed to handle. Some of the EA825 engine is divided into top and bottom sections, both made from aluminum alloys. The top section is die-cast for precise assembly, while the bottom is sheet metal, housing the oil drain plug and oil level temperature sensor. The timing chain cover, also aluminum, contains the engine speed sensor and crankshaft oil seal. These components are sealed with liquid gaskets to prevent leaks, ensuring reliable operation and easy maintenance access. Forged steel crankshaft is a key component, designed for strength and smoothness. It's supported by 5 main bearings with the cylinder bank set at a 90-degree angle. Opposing cylinders share the same bearing journal, optimizing balance and reducing vibration. This robust design allows the engine to handle high torque and power while maintaining reliability and longevity, essential for both performance and everyday driving. Crankshaft bearings use advanced IROX technology, meeting the demands of hybrid drive and start-stop operation. These 3-layer bearings consist of a steel backbone for stability, a soft metal carrier substrate, and a polymer-based top layer with fillers for optimal wear resistance. This construction ensures smooth operation, reduces friction, and extends bearing life, contributing to the engine's overall efficiency and reliability. Control the longitudinal movement of the crankshaft. 4 thrust washers are installed on the 4th bearing. These washers with oil grooves facing the crankshaft ensure precise axial control. This setup minimizes unwanted movement, reducing wear and maintaining the alignment of the crankshaft under various operating conditions. Such attention to detail is vital for the engine's smooth and reliable performance. Pistons are cast and mounted with a slight offset to minimize noise. Each piston features intake and exhaust valve recesses of different sizes, tailored for optimal combustion. The pressure side of the piston is more rigid, ensuring a defined wear pattern, while the counter-pressure side is softer for better adaptation. This results in different pistons for each cylinder bank, enhancing performance and durability. The piston rings and pins are also engineered for strength and longevity. Connecting rods are made from high-strength steel with a trapezoidal crack design for maximum durability. The upper end uses a copper alloy bushing, and the bearings are constructed from steel bismuth bronze and a thin bismuth crystal lining. Installation requires precise alignment of weight classes and markings to ensure balance and smooth operation. This meticulous approach guarantees the engine's reliability and performance under high loads. Belt, pulley, and vibration damper are secured to the crankshaft with a single bolt and dowel pin for precise positioning. A diamond-coated washer ensures proper friction and alignment. The damper housing is forged steel, while the inertia ring is aluminum, providing strength and resistance to deformation. This assembly helps reduce engine vibrations and supports the smooth operation of ancillary drives. Engine speed is monitored by a sensor located in the timing chain cover, which reads signals from a magnetic ring on the drive plate. This setup ensures accurate detection of crankshaft position and speed, which is crucial for engine management and timing. Reliable speed detection supports optimal performance, fuel efficiency, and emissions control. Cylinder heads are packed with advanced technology: double overhead camshafts, 4 valves per cylinder, roller cam followers, and an integral exhaust manifold. The hot side-inside layout places the turbochargers within the V of the engine for improved efficiency. Direct injection, Audi's valve-lift system, and hardened valves further enhance performance and durability. The design also supports cylinder-on-demand (CODI) operation, allowing selective cylinder deactivation for fuel savings. Reduce noise, 2-part insulating mats are installed over the cylinder head covers, effectively dampening high-frequency sounds from injectors and fuel pumps. The covers also house essential components like camshaft adjusters, ignition coils, and hall sensors. Proper installation order is crucial, as some parts are located beneath the insulating mats and must be fitted before the mats are in place. Valve gear features roller cam followers, sodium-filled exhaust valves, and monometallic intake valves with hardened seats. The springs are simple cylindrical shapes, and the system is designed for durability and efficiency. This setup ensures precise valve operation, reduced friction, and optimal combustion, contributing to the engine's high performance and longevity. Each camshaft housing is tailored for its cylinder bank, with 5 sleeve bearings and a central axial bearing. Components like ignition coils, cam actuators, sensors, and fuel system parts are integrated. Bearing caps and housings are matched by identification numbers to ensure correct assembly, maintaining precise alignment and smooth camshaft operation. Engine uses 4 composite camshafts, each with pressed-on end pieces and movable cam elements for the cylinder-on-demand CODI system. High-pressure fuel pumps are driven by the exhaust camshafts, and center wheels provide position feedback. The movable cam elements enable selective valve operation, allowing the engine to deactivate cylinders for improved efficiency under light loads. Cylinder-on-demand system allows the engine to shut off 2 cylinders per bank under low load, improving fuel efficiency and reducing emissions. This is achieved by closing the intake and exhaust valves and cutting fuel and ignition to cylinders 2, 3, 5, and 8. The transition is seamless, with active engine mountings minimizing vibrations, so occupants barely notice the change. The system operates based on engine temperature, torque, gear selection, and other criteria. OD activation depends on factors like coolant temperature, engine torque, gear selection, and battery voltage. The system operates in 3 phases, moving cam elements from 0 to full lift. Actuator pins and ball spring mechanisms lock the cam elements in place, ensuring precise valve control. This sophisticated mechanism allows the engine to switch between full and partial cylinder operation efficiently. All camshafts are equipped with hydraulic adjusters, providing a 50-degree adjustment range for optimal power, torque, and emissions. Intake camshafts lock in the retard position when off, while exhaust camshafts lock in the advanced position. This dynamic timing system, combined with internal exhaust gas recirculation, ensures the engine operates efficiently across all conditions. Camshaft drive system is located on the transmission side, with a crankshaft gear driving an intermediate gear, which then drives the camshafts via simplex chains. The intermediate gear acts as a tensioner, reducing noise. Multiple sensors and adjustment valves monitor and control the timing, ensuring precise synchronization for smooth engine operation. Setting the correct timing is crucial. The engine's basic position is achieved when cylinder 1 is at TDC, with locking pins securing the crankshaft. Camshaft adjusters must align precisely with housing projections, and trioval chain sprockets help minimize dynamic forces. This careful alignment ensures smooth running and optimal performance. A water pump drive shaft is mounted in sleeve bearings and driven by a tensioning gear connected to the crankshaft. During installation, the tensioning gear must be pre-tensioned using a special locking pin. This setup ensures reliable coolant circulation and contributes to the engine's efficient thermal management. Crankcase ventilation system uses oil separator modules on each cylinder head cover to filter blow-by gases. These gases are channeled separately for each bank, with intake points upstream of the turbochargers and in the intake manifold. Non-return valves regulate airflow based on pressure, and the system is managed by the ECM to handle large volumes of blow-by without oil loss. This design ensures clean operation and protects engine component. Filtered blow-by gases are directed into the intake manifold, where a PTC heater element prevents freezing under extreme conditions. The ECM controls the heater based on engine parameters, ensuring reliable operation in all climates. This attention to detail helps maintain engine performance and longevity even in harsh environments. The oil separator collects separated oil in a tray below the separator, directing it through channels back to the sump. A gravity valve ensures oil drains only when appropriate, preventing sump oil from entering the separator during pressure fluctuations. This system maintains oil cleanliness and supports efficient crankcase ventilation. PCV system uses two non-return valves to prevent excessive vacuum in the crankcase. Fresh air is drawn in before the throttle valve, and the flow is regulated by the ECM via the crankcase ventilation valve. This setup ensures proper ventilation under all operating conditions, protecting engine seals and maintaining optimal pressure balance. Fuel tank ventilation is managed by the ECM, using purge regulator valves and pressure sensors to control vapor flow from the charcoal canister. When a vacuum is present, vapors are vented into the intake manifold. Under boost, venting occurs before the turbocharger. This system ensures compliance with emissions standards and prevents fuel vapor loss. When no vacuum is present in the intake manifold, suction jet pumps use the Venturi effect to draw fuel vapors from the charcoal canister into the turbocharger intake. This clever use of pressure differentials ensures effective fuel vapor management under all engine loads, supporting clean operation and emissions control. Single-vane vacuum pump, driven by the inlet camshaft, supplies vacuum to key components: the coolant pump, turbocharger actuators, and brake servo. Electro-pneumatic actuators and changeover valves are controlled by the ECM, ensuring precise operation of the turbocharger bypass flaps and coolant flow. This integrated system supports both performance and safety. The oil circuit is designed for minimal pressure loss and optimal flow. Key features include a fully variable vane cell oil pump, piston cooling jets, and a thermostat-controlled oil cooler. Oil is distributed through galleries to all critical engine components, ensuring reliable lubrication and temperature control under all conditions. Vane cell oil pump is chain-driven by the crankshaft and features a guide rail and tensioner for smooth operation. It includes a pressure regulation valve and a suction pipe with an integrated strainer to ensure consistent oil supply, even during dynamic driving. The pump's compact design and precise control contribute to the engine's efficiency and longevity. Piston cooling is managed by a solenoid valve controlled by the ECM. Cooling is only activated when needed, based on engine RPM, torque, and oil temperature. This targeted approach reduces unnecessary oil flow, improving efficiency while protecting pistons under high load or temperature conditions. The oil system incorporates multiple sensors and actuators: oil temperature, pressure, and level sensors, as well as pressure regulation and piston cooling control valves. These components provide real-time feedback to the ECM, enabling precise oil management for optimal engine protection and performance. After passing through the oil coolant heat exchanger, oil flows into a plastic filter module with a bypass valve. The filter module is easy to access and replace, and a stainless steel heat shield protects it from turbocharger heat. This design ensures clean, cool oil reaches all engine components, supporting longevity and performance. Oil from the main gallery supplies the camshaft bearings, hydraulic compensation elements, high-pressure fuel pump, and vacuum pump. Branch ports ensure each component receives adequate lubrication, while the main gallery in the head cover distributes oil to the camshaft adjusters and large bearings, supporting smooth and reliable operation. Ancillary components like the alternator and air conditioner compressor are driven by separate, maintenance-free belt drives. Automatic tensioners keep the belts properly adjusted, and both drives are powered by the crankshaft's vibration damper. This setup ensures reliable operation of all essential accessories with minimal maintenance. V8 engine's cooling system is designed for efficiency and emissions reduction. A thermal management system activates various cooling circuits as needed, helping the engine, transmission, and passenger compartment warm up quickly. This approach reduces fuel consumption and emissions while maintaining optimal operating temperatures for all components. Thermal management relies on input from sensors monitoring coolant and oil temperature, engine speed, torque, and more. The ECM coordinates the activation of coolant pumps, thermostats, and valves to achieve the desired temperature profile. This ensures efficient engine operation, passenger comfort, and compliance with emissions standards. Coolant circuit features dedicated supply and return galleries, connecting pipes and distribution channels for ancillaries, turbochargers, and the oil coolant heat exchanger. Restrictor pins and web cooling channels ensure even temperature distribution, preventing hotspots and maintaining engine integrity under all operating conditions. Audi 4L V8 TFSI engine from the EA825 series is a showcase of modern engineering, blending performance, efficiency, and reliability. From its advanced cylinder block and crankshaft design to its innovative cooling, oil, and ventilation systems, every aspect is optimized for high output and low emissions. The integration of smart sensors, actuators, and control modules ensures precise operation and easy maintenance. This engine sets a new standard for V8 performance in luxury vehicles. As we wrap up, it's clear that the EA825 V8 TFSI engine is not just about power. It's about intelligent design, efficiency, and adaptability for future automotive needs. Audi's commitment to innovation is evident in every detail, from material choices to electronic management. This engine paves the way for even more advanced powertrains, ensuring Audi remains at the forefront of performance and sustainability in the years to come.